Okay, let's dive in. When you hear jute, maybe, like me, you picture those rough, kind of old-school burlap sacks.
Yeah, the classic image. But jute, it's often called the golden fiber, especially important over in Bangladesh.
Yeah.
It's inherently pretty amazing stuff.
Yeah.
It's renewable, it's biodegradable, super sustainable just as it grows. And now, people are using it for all sorts of upholstery, curtains, even in, like, construction composites. It's really versatile.
Which sounds ideal, doesn't it? A natural, eco-friendly fiber. Perfect for where we want to go sustainably. But here's the catch, and it's a big one. While the plant is green, turning that raw fiber into fabric, you can actually dye. Well, traditionally, that process is pretty rough on the environment.
That's exactly the hurdle, yeah. Conventional textile processing for jute, specifically the prep work before dyeing the pretreatment, uses a load of harsh chemicals.
Like what sort of things?
Well, strong alkalis, think sodium hydroxide, bleaching agents too, plus high heat, lots of water, and then rinse after rinse. Yeah, it uses tons of water, and the big problem, creates all this polluted wastewater full of chemical gunk. It really holds jute back from being that truly sustainable textile we need for modern uses.
And that environmental snag is exactly what we're digging into today. We've got a research paper here just published in Green Technologies and Sustainability. And it explores what could be a real game changer. A totally chemical-free way to prep jute fabric for dyeing, just using high heat and water.
Exactly. So our mission, really, in this deep dive is to unpack this study for you. We'll look at, why you even need pretreatment, how the old chemical way works, and then really get into this new chemical-free idea.
And see how it stacks up.
Precisely. We'll look at the experiments, the results, and the surprising thing is, this chemical-free way doesn't just, match the old way in some respects. It actually seems to improve things in others. So is it viable? Is it sustainable? And crucially, is it effective? That's what we'll explore.
Okay, let's start right at square one then.
Yeah.
Why does jute need this pretreatment anyway, before you even think about color?
Good place to start. So raw jute fiber isn't just pure cellulose. It's got a lot of other natural bits mixed in waxes, pectin, lignin, hemicellulose.
Okay.
And this stuff tends to be hydrophobic, repels water. So trying to dye raw jute is kind of like, trying to paint on a greasy surface.
Ah, right. The dye just wouldn't soak in evenly or maybe at all.
Exactly. It wouldn't penetrate. So pretreatment is all about getting rid of those water-blocking barriers, making the fiber thirsty, basically. Opening it up so the dye can get in deep and give you a nice, even color.
Gotcha. So how does the standard traditional chemical method do that?
Well, the paper outlines a common process. It involves steps called scouring and bleaching. The key chemicals are things like sodium hydroxide, NaOH, that's a strong alkali, which is really good at breaking down and dissolving impurities, particularly the lignin and pectin.
Okay.
And then you often have hydrogen peroxide for bleaching to lighten the natural color. This is typically done around, say, 90 degrees Celsius.
Still pretty hot.
Oh, yeah. And then it needs loads of washing and neutralizing steps afterwards to get all those leftover chemicals out. It works, it cleans the fiber, but like we said, big environmental footprint.
Right. So chemicals are the sort of power wash in the old method. Now tell us about this chemical-free alternative they tested.
Okay, this is where it gets really neat and kind of simple, actually. The method they proposed uses only water.
Just water?
Just water, no added chemicals, zip. They treat the jute fabric in a pressurized system because they go above boiling point using just water at 130 degrees Celsius for an hour.
Whoa, 130 C.
Right.
So significantly hotter and under pressure to keep it liquid.
Correct. And the researchers basically hypothesized that at this high temperature and pressure, the water itself starts acting differently. It does this thing called autoionization.
Okay.
Where a tiny fraction of water molecules split into ions, hydrogen ions, hydroxide ions. The idea is that these naturally formed ions, plus the intense heat, are enough to cause a partial breakdown of some key impurities, especially things like hemicellulose and pectin.
So it's not like the brute force chemical attack.
No, it's more subtle. It's the heat and the water's own slightly altered chemistry doing enough work to sort of open the door for the dye without needing added chemicals.
And the environmental win there seems obvious.
Huge. You just cut out all the issues with sourcing, handling, disposing of hazardous chemicals. Your wastewater is suddenly much, much cleaner. Okay, you still need energy for the heat, but the reduction in chemical pollution, massive. And potentially cheaper, too. No chemicals to buy, less complex waste treatment.
Okay, the concept sounds brilliant in its simplicity. But, the big question, does it actually work as well? How did they compare it?
Right, that's what the experiments were all about. They set up a direct comparison, took samples of jute fabric, treated some the conventional chemical way, treated others with this new hot water method.
Okay.
Then they dyed both batches using two common types of dye, a reactive red and a basic green, and ran a whole battery of tests to see how they perform side by side.
Let's start with absorbency. You said that's key for dyeing.
Yeah.
How did that look?
Yeah, they measured that in a few ways. The simplest is the drop test. How fast does a water droplet soak in? For plain water, the conventional chemical samples absorbed it in about 4 seconds.
Pretty quick.
Yeah. The chemical-free ones were a bit slower, around 6.5 seconds. Similar pattern with dye droplets, about 11 seconds for conventional, 13 or 14 for chemical-free.
Okay. So it is a bit slower, at least on that first contact.
Yeah.
Does that matter much in practice, you think, if it takes a couple extra seconds for the first drop?
That's a fair question, but the paper suggests maybe not critically. They also did other tests like spot and column absorbency, which look more at how water spreads and wicks through the fabric.
Oh, okay.
And in those tests, the results were actually very close between the two methods. So while that initial surface absorption might be a tad slower, the overall ability of the fabric to take up liquid seems quite comparable. It suggests the hot water is effectively clearing out enough impurities, maybe just leaving the surface slightly different than the chemical scour.
Interesting. Okay, so absorbency is comparable overall. What about the main event, the color itself? How did that turn out?
This is where things get really interesting and actually kind of surprising. They measured color strength KS values. Basically, higher number means deeper, stronger color.
Right.
For the reactive red dye, the chemical-free samples actually showed higher color strength, an average KS of 18.2 compared to 15.8 for the conventional.
Wait, hang on. The chemical-free method gave a stronger red color, using just water.
Yep, that's what the data showed. Now, for the basic green dye, the values were much closer, 25 for chemical-free versus 26.2 for conventional, very similar.
Wow, okay, but still, getting a more vibrant color with one dye using no chemicals,
Yeah.
that's pretty remarkable. Not what you'd intuitively expect.
It's a key positive finding, absolutely. They also looked at whiteness, how much that natural yellowish jute color was removed before dyeing. Here, the conventional method did better. The chemical-free samples were a bit less white, maybe 149 versus 159 on their scale for the reactive dyed ones, and the difference was bigger for the basic green samples.
So the chemical-free method doesn't bleach it quite as much initially?
Correct.
But it still allows for really good, maybe even better color intensity when you actually dye it. That feels like a fantastic trade-off, getting rid of the harsh bleach.
Absolutely. I mean, the main goal of pretreatment is getting the dye in effectively, right? Not necessarily achieving maximum whiteness first. And on dye uptake, it clearly performs very well.
So let's try and get under the hood a bit. Why is this happening? What did they find when they looked at the actual fiber structure? You mentioned FTIR and SEM tools.
Right, these give you a closer look. FTIR looks at the chemical bonds. It showed the high-temp water treatment did indeed disrupt some of the internal hydrogen bonds in the fiber. And crucially, it caused that partial breakdown of hemicellulose and pectin we talked about.
The dye blockers.
Exactly. Now, the FTIR also showed the conventional chemical method removed more of these impurities, which makes sense. It's more aggressive. But importantly, the chemical-free method seemed to leave the lignin structure, which gives the fiber its strength mostly untouched.
Okay, so the hot water is kind of selectively loosening things up, getting some of the gunk out, especially hemicellulose and pectin, but leaving the main structural bits, the lignin, alone.
That's a good summary, yeah. That partial removal and the disruption of the internal structure seems to open up pathways for the dye molecules to get in, which explains the good color results and decent absorbency.
And what about the surface? What did these SEM, the microscope images, show?
That was interesting, too. The SEM pictures showed the conventional chemical treatment tended to leave the fiber surface relatively smooth.
Okay.
But the chemical-free, high-temperature water treatment, that resulted in a noticeably rougher surface. You could actually see more micro cracks and some sort of deposits on the fiber surface after the hot water treatment.
Roughness. Cracks. That sounds a bit worrying. Does that mean the fabric is weaker? More brittle?
That's the logical concern, isn't it? You see cracks under a microscope and think, uh-oh. But this leads directly to the next set of tests they ran, which specifically measured the fabric's strength.
Okay, tensile strength. How did it hold up?
And this is probably the other really big positive surprise from the study.
Don't keep us in suspense.
The samples treated with the chemical-free method, the ones with the rougher surface, actually had a slightly higher average tensile strength, about 150 newtons compared to 147.5 for the conventional ones.
Get out. Stronger.
Stronger. And not only that, the elongation, how much it could stretch before breaking, was also a little bit higher for the chemical-free samples.
Wow, okay, that is completely counterintuitive. The method that looks rougher under the microscope actually produces a stronger, slightly more elastic fabric than the one using harsh chemicals.
It really is counterintuitive, and it's hugely significant. It suggests that whatever surface effects the high heat is causing, they aren't compromising the overall structural integrity. In fact, maybe they even enhance it slightly.
Oh.
Well, perhaps it links back to that FTIR finding, leaving the lignin core intact might be key. Maybe the aggressive chemicals, while smoothing the surface, actually do more subtle damage to the fiber's core strength that the hot water avoids. So those surface cracks seen in SEM, maybe not detrimental to the overall performance, the fabric is actually more robust.
That's incredible. A major win for the sustainable option. What about keeping the color on? Did they test how well it holds up to washing and wear?
Yep, color fastness tests. They checked wash fastness, perspiration fastness, and rubbing fastness. Generally, the results were very comparable.
So no major fading or bleeding issues with the new method?
Not really. For washing, the color change was similar, maybe grade 3-4 on the 1 to 5 scale, where 5 is perfect.
Yeah.
Staining on other fabrics was also pretty similar overall. Perspiration tests, excellent results for both methods, grade 4 mostly.
Right.
Rubbing fastness was interesting. The chemical-free reactive red samples actually showed slightly better dry rubbing fastness than the conventional ones.
Another win.
Yeah. Wet rubbing was generally good for both, maybe conventional slightly better in one specific case, but overall the color durability is definitely maintained, even slightly boosted in some ways by the chemical-free approach.
So the color goes on well, sometimes even better, it stays on well, and the fabric is stronger.
That's the package, yeah. Pretty compelling.
Okay, let's just pull all this together then. What's the big picture takeaway from digging into this research?
I think the main conclusion is pretty powerful. This study really demonstrates that a chemical-free, high-temperature water pretreatment for jute is, well, viable. It's a sustainable alternative that works.
And not just works, but...
Right. It achieves comparable or even better performance in really key areas like color strength for certain dyes and, crucially, tensile strength. It makes the fabric stronger and a bit more elastic while keeping the color just as durable.
And for you listening, the impact here is potentially huge, right?
Absolutely. This points to a way to make jute textiles, which are already from a sustainable source, much, much greener in their processing. Cutting out those chemicals means less water pollution, less hazardous waste. That's a big deal for the textile industry.
Plus, you might get a better product.
Exactly. That bonus finding, stronger, more durable fabric from an eco-friendly process, that's the dream combo. It shows sustainable methods don't always mean compromise. Sometimes they can actually lead to improvements.
Now, they were those small things, like the slightly slower initial water drop absorption, the rougher surface under the microscope.
True, there are slight differences, but honestly, when you weigh those against the massive environmental pluses and the gains in strength and color vibrancy, they seem like pretty minor trade-offs, wouldn't you say?
Yeah, definitely feels that way. So it's a really promising proof of concept. Did the researchers suggest what should happen next? Where does this go from here?
They did. They highlighted the need for optimization, maybe tweaking the temperature, the time, the pressure to really dial it in perfectly. They also suggested trying this on other natural fibers. Could it work for cotton, flax?
Good question.
And importantly, doing a full life cycle assessment, an LCA, to really quantify the environmental savings when you scale this up for mass production compared to the old chemical ways.
This really does make you think, though. If this study shows that just heat and water, used smartly, can replace harsh chemicals and actually improve a material like jute in some ways, what else could this approach be used for? What other industries, what other materials are stuck using polluting chemical processes that could maybe, just maybe, be reimagined with just heat and water? It really sparks the imagination about what other sustainable innovations might be hiding in plain sight.